All right, greetings everyone. Welcome to the first part of the video for section 6.1, delving into chapter 6 now. And we'll start by looking at sine and cosine and other trig functions as functions and kind of how they behave. So I'm going to start off with an example with a Ferris wheel. And I don't know about the rest of you, but Ferris wheels are not one of my favorite rides. When I was younger, I used to be extremely scared of heights, so I actually haven't been on that many Ferris wheels. Maybe y'all have different feelings about them. But even with that, let's look at an example where we might be wondering how we can build a mathematical model, i.e. a function, to describe the height of a car on a Ferris wheel after a particular amount of time, t. So it looks like the way we're setting things up here is we want these heights here, these h's, those would be our output values. And then the t's here, the times, that would be our inputs. So we want to be able to figure out at a certain time, what will the height be? So if we input a time. Now, if you think about how a Ferris wheel works, that might be a tough question to answer, because notice you start at a certain height, you go around the Ferris wheel to a particular height, maybe the peak height, but then what happens after that? Well, you go back down, and then you might repeat that process again and go through the same sequence of heights. So as you can imagine, this might involve or require that we can draw a function or work with a function that might be different than ones we've seen before. So what I'm going to do then is look at a video that is going to allow us to kind of look at a model of how we might do this. So I'm going to make this full screen. All right, let that go. Okay, so before the video starts, I want to point out what is going on here. So notice this red dot on the Ferris wheel. That's going to be like our person in a car or us. And what they've got here on their sets of axes, along the horizontal axis here, those are going to be times, so those would be the t's. And then the vertical axis, that's going to be the heights. So that'd be the values for h. And if you watch this little red dot right here, that's going to trace out as time passes, so it's going to move this way. It's going to trace out the heights on the vertical axis. So watch that as it goes. Okay, so you can see it starts to move up as the person on the Ferris wheel moves up, and they hit that max height, and then they come back down as the Ferris wheel moves down. And then notice they're about to get back to the same starting point, but then they continue on again and go through the same motion. Okay, and it could continue on from there. And hopefully what you notice, what happened in the graph there, is kind of a repeating shape, right? Again, we started at the bottom, went up to the peak, and then back down, and up to the peak again, then back down. You can imagine that that process or that pattern could continue. Okay, so we see a pattern forming in what's going on with the shape of the function. Well, when we have a function like that, where there's a repeating pattern in its shape, we have a special name for that. That's called a periodic function. And so the idea with a periodic function is one where a specific horizontal shift, which we call p, and p usually stands for the period, okay, results in the original function. So as an example of that, here in the picture, they have a function they're calling f of x. And notice this is a periodic function, because if we take, say, this piece right here, okay, if we shifted it over this distance of p that they've highlighted here, notice we end up with the exact same shape. It'd be the same thing if we shifted it backwards that much, we'd end up with the same shape here. So we see that this is also a repeating, what we call periodic function. All right, and that may lead us to wonder, do we already know any periodic functions? Well, it turns out we do. We just may not have thought of them this way yet. So we're going to start by looking at the function f of x equals sine of x. So basically we're looking at the sine function as a function. And notice here on the set of axes, we've labeled the horizontal axis with different values along the unit circle in radians. Okay, both some positive and some negative numbers. I'm also going to label the vertical axes with some numbers. I'm going to call this one up here +1, and this one down here -1. And we're going to plot some points in a second. But before I do that, I do want to talk about why we're using radians here. And the reason simply is for convenience of using smaller numbers, because you may notice that if I do pi/2 in my calculator to find a decimal answer, that's the same as 1.571. We know pi is about 3.14. 3pi/2 is about 4.712. And then 2pi is about 6.28. So notice those are pretty reasonable, fairly small numbers to use. If we were to do this plotting in degrees, well, think about the numbers we would need to use. Pi/2 is 90 degrees. Pi is 180 degrees. 3pi/2 is 270 degrees. And 2pi is 360 degrees. So notice those numbers get really large. So generally when we're graphing trig functions, we're going to work in radians. Okay, and this will be important if you try to graph some trig functions on your calculator. You'll want to make sure you're in radians mode. All right, so let me set up my table here. So my x's and my f of x's. And start by plugging in the values along the horizontal axis there. So we have 0, pi/2, pi, 3pi/2, and 2pi. And if you have a unit circle handy, or if you have it memorized already, you can reference that as we go through this. So if I plug in 0 for x up here into my function, I'll have f of 0 equals sine of 0. Looking at the unit circle, we see that's 0. If we plug in pi/2, we'd have f of pi/2 equals sine of pi/2, which gives us a +1. At pi, plug that in, sine of pi is 0. At 3pi/2, we plug that in, we'll get -1. And then plugging in 2pi there will again give us 0, because it's the same as plugging in 0. So from that, we can go ahead and plot those points. So we have 0, 0. We have pi/2, 1, pi, 0, 3pi/2, -1, and then 2pi gives us 0. So when we connect the dots, we get something that looks like this. However, I just kind of teased this as being about periodic functions, so it doesn't look very periodic. So let's see if there's something more we can do, and let's go ahead and plug in the negative angle values now. So we'll plug in -pi/2, not like that though. Here we go. -pi/2, -pi, -3pi/2, and -2pi. Let's plug these in. -pi/2 is the same as 3pi/2, so plugging that in for sine, we get -1. -pi is the same as pi. Plugging that in gives us 0. Negative 3 pi over 2, that's the same as pi over 2, so plugging that in gives us 1, and this should say negative 2 pi. Plugging that in, again, gives us 0. And now if we plot those points, so negative pi over 2, negative 1, negative pi 0, negative 3 pi over 2, 1, negative 2 pi 0, and connect the dots, hopefully what you see now is a much more periodic function, right? Because notice if we take that left-hand piece there, so say this shape here, and look at the right-hand piece, okay, notice that what I've highlighted there in red and orange are basically the same shape, right? They're just shifted over to the left or right. So we see that sine is in fact a periodic function. All right, whoops, I should not have erased what I had there. I apologize for that. So the next question I want to know is if sine is even, odd, or neither, what its domain and range are, and also what the period is. And remember, period is that distance over which we see one of those repeating patterns. Okay, well, first things first, having to do with even or odd or neither. Recall that a function is even if we can reflect it across the vertical axis and it'll line up with itself. In this case, we see that won't work with sine because notice if I took that piece that I just highlighted, reflected it over the vertical axis, I would get something that looked like this, which is not part of the green graph. So therefore, the function is not even. It's odd if we can reflect it over both axes and then get a function that looks like the original one we started with. And notice if we do that with, say, this piece here, we can reflect that across the vertical axis. That would give us this. And then reflect it across the horizontal axis, and notice it lines up with itself. And we could do that with the other pieces as well. So what we see is that the sine is actually an odd function. Domain and range, well, notice for the domain, remember that has to do with values along the horizontal axis. And it looks like from the graph, since we see arrows continuing to both the left and the right, and we know this pattern is going to repeat to the left and the right, it looks like our domain here could be all real numbers, which we'll give in interval notation as negative infinity to positive infinity. And then the range, recall, is all the output values. Well, notice again, if the function is repeating this pattern, the highest value it ever gets to is up here, and the lowest value it ever gets to is down here. And that lowest one being -1, that highest one being +1. So we see that the range is going between -1 and +1, and it is actually passing through those values, so we'll put brackets around them. And then the final thing is the period of the function. And remember, the period is the distance over which one of those repeating patterns is happening. And notice that here we see one of those, it starts at a value of 0 and goes to 2 pi. So it looks like the period might be 2 pi, and we also see that if we start here and look at the distance of what are these, the distance from -2 pi to 0 is also 2 pi. So we see then that the period of a pi function, or excuse me, a sine function is just 2 pi. Okay, which hopefully isn't too surprising because it's as if we're doing one full rotation around a circle. All right, that's it for now. Thank you for watching.